Okay, let us begin. Welcome everybody to this week's Majorana-Raychaudhuri seminar series. Our first speaker today is Sam Young from University Pisa, and he is going to tell us about relics from the dawn of time and ripples in the fabric of space-time. Maybe I send you a reminder when 5 minutes are left.
Yes, please, thanks. Okay, you're okay if I start sharing now?
Yes, and if there is a
Yeah,
question from YouTube, I will ask. I will put it.
okay, yeah, please do. Okay, great. I hope everyone can see the talk. So thank you very much for the invitation. It's a pleasure to be here and talk about primordial black holes and gravitational waves and some of my research on them. So before I get started, I'll just use the opportunity to advertise another online seminar series if you're interested in hearing more about primordial black holes. They normally happen on the first Monday of the month at 3 p.m. European time. We're on the summer break now until October, but if you're interested, you can either send me an email to that email address or search for Google group zooming-pbhs. That should be H and not an X, sorry. And you could, Anish has my email, so if you don't get the email written down, you can contact him and he'll forward it to me as well. Okay, so what am I talking about today? Well, by the end, I'll hopefully answer some of these questions, well, all of these questions. So the first question is, what is dark matter? And, how do we know it's there? How does it fit into the kind of standard model of cosmology that we have today? Secondly, what are primordial black holes and why should you care? And what is the evidence for and against primordial black holes? Then I'll talk about what are scalar-induced gravitational waves and how they affect or how they're useful for constraining the early universe, and how do we calculate the abundance of primordial black holes. Now, I believe Dr. Burns gave a talk last week on a similar topic, so I'm going a little bit more in depth into kind of the abundance and how we calculate their abundance this week, and a kind of a less of an overview, because I think he should have given quite a good overview last week. Okay, so the first thing is what do I do? What is my area of study? And you can be broadly classified as astronomy, astrophysics, or cosmology, and definitely not under any circumstances, which I hear a lot when I tell people I do cosmology. They think I'm in cosmetology, which is kind of the science of makeup, or they think I'm in astrology, which is the study of star signs and how that you can use that to predict what's going to happen. And obviously, it's neither of those things. Okay, so people generally classify themselves as an astronomer, which is the branch of science that deals with celestial objects and the universe as a whole, or an astrophysicist, where they're mainly concerned with the physical nature and the physical models that describe those celestial bodies, or a cosmologist, which is the science of the origin and development of the universe. Now, in reality, most people are kind of a mix of all three, and people don't fit neatly into one of those things. There are also different types of cosmologists. People generally classify themselves as an observational cosmologist. So are they doing observations? Are they a computational cosmologist? Do they mostly run simulations and work with large codes? Or are they theoretical cosmologists, which means that they mostly do with building theoretical models which describe the universe? So the first question is, what do we know about the universe? What's the standard model of cosmology tell us about the early universe? And the basic idea is that the universe is expanding at the moment, and it's often said that it all started with a Big Bang, but we don't really know that. So let's really quickly say what the Big Bang theory says. It says that the universe is expanding. We can see expanding. If we look up and we measure how distant stars and distant galaxies are moving, they all seem to be moving away from each other, which means that, as a whole, the universe is expanding. And that means that in the past, it used to be much smaller, hotter, and denser. Okay, so I generally prefer to think of the Big Bang as a description of what the universe is doing now rather than how it began. So it's a giant explosion. Everything's all flying away from each other, and that's still ongoing. The Big Bang Theory doesn't say how the universe began. So most modern cosmologists don't think that the universe started as a singularity which exploded. That's kind of outdated and hasn't really been believed for 30 to 40 years. So the question is kind of then what was the early state of the universe? And inflation is the leading hypothesis at the moment, where the universe went a period of rapid accelerated expansion, And then there was kind of phase shift, and then we went from that period of cosmological inflation, and then the universe after that changed, and we call that reheating. Universe reheated, and we ended up with a universe similar to the one we see today. And the question is, okay, if the universe used to be much smaller and denser and hotter, we know that hot things glow. So if the universe used to be much hotter, why can't we see that glow when we look up? Why isn't the whole night sky glowing? And the answer is that actually it is. We can see the glow, it's just not in visible wavelengths anymore. So as the universe expands, the light traveling through it also, the wavelengths expand as well, and they redshift into longer and longer wavelengths. So we can see that afterglow of the Big Bang happening, and we can see, that fireball universe back in the distant past. We can just see it in microwave wavelengths, in what's called the cosmic microwave background radiation. And this is the picture that's normally shown when you picture the CMB. This is the one everyone always thinks of. And the question is this, an accurate representation of the CMB? And the answer is yes, of course it is. This is taken from the Planck satellite, this particular image, and it's got very, very precise maps of the temperature of the CMB at different scales. But it's also quite a misleading picture, because you look at it and you think, oh, there are, very bright spots on it, or very high temperature spots and very cold spots on it. So it's not the best picture of the CMB. The picture of the CMB I prefer is this one. And I prefer this because I think it gives a much better idea of what the early universe, or what the CMB actually looks like. The temperature perturbations are still there, but they're just absolutely tiny. So if I look at the temperature of the CMB, it's 2.73 Kelvin everywhere, and there are very, very small perturbations to that on the order of 0.000001. So on the order of 10 to the minus 5. So this isn't just a green oval. I've actually downloaded this data from the WMAP collaboration website, but I much prefer this image of the cosmic microwave background. So how did we go from something that looks like this? It's the same everywhere. How did we go from something that looks like the universe today, where it's obviously not the same everywhere, and you can kind of prove to yourself that it's not the same everywhere if you look to your right and you see what's over there. In my case, there's a window. On my left, there's a wall. On larger scales, some places in the universe have galaxies, and some are just giant voids. So how did we go from this universe, which was pretty much the same everywhere, to the universe today, which is very, very asymmetric? It doesn't have the same thing everywhere. The base case is that we have quantum fluctuations in the very early universe, which give rise to small perturbations in the early universe. So this is a picture of kind of the early universe at relatively early times, okay, at the moment. And those perturbations are going to grow over time, forming the seeds of structure. Now, this is a simulation. And just bear in mind, I'm going to run the simulation forwards, and we'll see how those structures start to form in the universe. So there are slightly overdense regions, and because they're overdense, they have more gravity, and they pull all the kind of surrounding material into them, and they start forming this kind of structure that we can see starting to form here, that's known as the cosmic web, just because it's, all the different regions are connected with strands and filaments. That's called the cosmic web. And at the center of these, where we have kind of the bright spots appearing on the picture, that's where the galaxies will form inside the center of those halos of matter, and stars and planets will then go on to form inside those galaxies. So those original quantum fluctuations we see are the seeds that will later go on to form everything that exists in the universe today. So the question is, okay, well, what's the universe? What's in the universe? What's it made of? And there are kind of, three more or less basic constituents. Firstly is all of the kind of the normal matter that we know is out there, which, we can look around and we can see stars and planets and galaxies and things like that. And it actually turns out that if we look at that structure in the universe, less than 1% of all of the energy budget in the universe actually goes into making that structure. Okay. There's far more free hydrogen and helium around, which is still normal matter. Okay, that's this kind of red slice here. About 4% of the energy budget of the universe is in that normal matter, and most of that normal matter is just floating around in space doing nothing. Now, roughly a quarter of the universe is dark matter, and I'll talk a little bit more about what that is later. It's a type of matter which we can see its effects. We know it's there, but we can't see it directly with light. So we call it dark. And most of the universe is made of something called dark energy. Okay, and we really have very little idea what that is, but something is causing the expansion of the universe to accelerate. So there's energy out there somewhere causing that acceleration to happen, and we don't know what's causing it. And because we can't see it directly, it's called dark as well. So I'll talk a little bit more about dark matter, but not about dark energy for the rest of the talk. So dark matter is often called cold dark matter, and we believe that it makes up about 27% of the energy content of the universe. And we don't know what it's made of, but we can see its gravitational effects. We don't know much about it, but we do know that cold dark matter is cold and dark and matter, so it's pretty well named. But what do those three things mean? When we say it's cold, we mean it's moving around slowly, right? If it was hot, then the particles or whatever makes up dark matter could be moving around close to the speed of light, okay? And if that was happening, then we wouldn't see the structures forming that we see because all the matter in it would kind of stream out those halos. It's dark, meaning it doesn't interact with light, and it's matter, meaning that it seems to gravitate like matter. And the mass of whatever makes up dark matter is the least known thing in the universe. There are some models which describe it as having masses of 10 to the minus 22 electron volts, which is absolutely tiny, going up to, in the case of primordial black holes, hundreds or even thousands of solar masses. So spanning a huge range of energy scales. And I believe it's the thing we know the least in the universe. And then there's dark energy, which makes up most of the energy content of the universe. So how do we know if we can't see dark matter directly? How do we know that dark matter exists? And kind of a common thing you'll see written on the internet, or if you kind of read comments by people, you'll see comments like dark matter is just made up by scientists because their equations don't work. But there are a lot of good reasons to know that dark matter does exist. Okay, we've got galaxy rotation curves where we can look at kind of how fast objects are orbiting galaxies. And we can use that to kind of work out, okay, if they're orbiting at a certain speed, we can use that to work out the gravitational force acting on them, and that gives us an idea of how much matter is inside that galaxy. And it's a lot more than would just be made up by looking at the matter we can see. We also have gravitational lensing, where light will be curved by the gravitation of large objects like galaxy clusters. And we can use the amount that it's lensed to measure the amount of mass inside galaxy clusters. And again, that tells us there's much more mass there than we could see just with the available matter. And one of the most interesting ways is the bullet cluster. Now, this on the right is a kind of an image of the bullet cluster. And what's happened is two galaxy clusters have kind of collided with each other and passed through each other. Okay, and as they've collided with each other, so this one over here came from the left and is traveling came from the right and is traveling from the right to the left, and this one over here came from the left and is traveling to the right. And what's happened basically is that the normal matter in there has collided with each other and slowed down, and the dark matter in there has just kind of passed straight through each other, and it's caused, and they haven't collided with anything, and that means that the regular matter is now lagging behind the kind of the dark matter in these two clusters. And that we've mapped out where the dark matter is by looking for the gravitational lensing of the galaxies behind the cluster, so that a lot of the dots you can see in this are actually galaxies and things that are behind the cluster. And finally, we have the way that structure forms and evolves in the universe. And if we put into theoretical models, how much structure should we expect to see with the amount of just regular matter we can see? We see that there's not enough matter there to pull matter together to form galaxies and stars and things like that. So the question then is, okay, well, what's dark matter made of? And most models hypothesize that dark matter is some new type of particle. And that makes sense. Everything's made of particles. So there's some kind of matter out there that we can't see. So most people focus on the fact that there's, okay, some kind of new particle out there which doesn't interact with light that we can't see. And that's fine. And it just requires some extension to the very successful standard model of particle physics, which works very well as it is without any additional particles. But you can add things in. But could it be made of black holes, right? We know black holes exist. We know they are cold, right? They're not zipping around close to the speed of light generally. They're dark, and they gravitate like matter. And the answer is yes, dark matter could be made of primordial black holes, but it couldn't be the normal type of primordial black hole formed from dying stars. Basically, because that would have had to have meant that, if you started off with all the matter in the universe, most of that matter would have had to form black holes if it's going to make up dark matter. And then, you have to explain, how did all that matter form black holes? It's not possible. So if we can't be talking about black holes that come from dying stars, where else could the black holes have come from? Generally, to form a black hole, we need to crush a large amount of matter into a very small space. And one of the places that can happen is the cores of dying stars. So what we really need to form a black hole is an area of extreme density. So except in the cores of stars, where else in the universe do we get really high densities? And a better question to ask is, when else in the universe do I get extreme densities? And the answer is, in the very early universe, when it used to be much smaller and denser, the universe used to be dense enough to form primordial black holes. So primordial black holes are often called kind of relics from the dawn of time. And at very early universe, the universe used to be much denser and more than dense enough to form primordial black holes. Right, the density of regions of the early universe used to be much denser than even at very early times. I'm talking before 1 second. Used to be much denser than you need to form black holes today. And so it's possible that primordial black holes could have formed at such early times from collapsing density perturbations. And because it was so dense, there is theoretically no minimum mass that can form. And the earlier time that the primordial black holes formed, the lighter the primordial black holes that you can form. So if we start with, a period of cosmological inflation before the Big Bang. Sorry, 1 second. I'm just going to have to deal with this.
Non l'ho neanche toccata.
Right. Sorry about that. Let's go to the library because people aren't liking what I'm talking even in the co-working area. Okay, let's carry on. Okay, so the basic idea is that we can have a period of cosmological inflation, which is believed to be how the universe began, and quantum effects at that time create density perturbations, and on small scales you can form very large amplitude density perturbations, which can go on to collapse to form primordial black holes and create gravitational waves as well. So, why should we study primordial black holes? They're a viable. Sorry, everyone.
Ci stavano dei ragazzi che lavorano qua. Io l'ho lasciato per la Questo è proprio
Okay. Can everyone just be quiet, please? Thank you. Okay, grazie. Okay, grazie. Okay, sorry. So why should we care about primordial black holes, and why should you listen to me? Well, firstly, they're a viable cold dark matter candidate. They are cold and dark and matter, but we'll look at some caveats to that statement in a moment. They're a unique probe of the small scale early universe. So when we want to study the early universe, we can look at things like galaxy clusters or the perturbations we can see in the cosmic microwave background, and we can say what the universe used to look like on very large scales. But we have very little information about the small scales, right? It's hopeless to look at something like the solar system and try and work out what was there 13.7 billion years ago, when the universe, in the very early universe. So primordial black hole dark matter also wouldn't require any extensions to the standard model of particle physics, but does have kind of its own challenges and fine tuning that you need. We may have seen some evidence for them already in the LIGO Virgo Cagra black holes, the massive compact halo objects, which were seen in the late 90s. We've seen gamma ray bursts, which have been hypothesized to come from evaporating primordial black holes, and the early formation of supermassive black holes. And their presence may also explain a lot of unresolved problems in cosmology. For example, the nature of dark matter, as I just mentioned, the early formation of supermassive black holes, missing satellites, how the universe reheated, and so on. And my personal favorite, it's even been hypothesized that Planet 9, which is hypothesized to exist as a ninth planet in the solar system, could be a primordial black hole. And of course, there are other possibly more likely explanations for a lot of these, and none of these are kind of definitive proof that primordial black holes exist. And the reason why Planet 9 is my favorite kind of object is because it's the paper that kind of made this suggestion. Is the only one-to-one scale diagram I've ever seen of a celestial object in a paper, where you just have a one-to-one scale diagram of how big the black hole would be, about the size of a tennis ball. Primordial black holes, as I mentioned earlier, are currently at least unique probe of small scales. So because primordial black holes form from the collapse of density perturbations, the larger those density perturbations are, the more primordial black holes you have. So you can use constraints on primordial black holes to place constraints on the amplitude of density perturbations in the early universe. And the way we describe density perturbations in the universe is with the power spectrum. And basically, what we've got here is the wavelength, wave number on the x-axis. So from going left to right, we're looking at smaller scales this way, and we've got the power spectrum on the y-axis, which basically describes the scale of the amplitude of perturbations. So on the left, at the very largest scales, we've got very, very accurate constraints on primordial perturbations coming from the CMB, but only at the very largest scales, right? Where there are much smaller scales exist in the universe, and we don't have any way of constraining those apart from mostly primordial black holes, which are these two kind of roughly horizontal lines here. Now they constrain a much larger range of scales, but because we need much larger amplitude perturbations to form primordial black holes, the constraints are much weaker. Okay, and they're also somewhat model dependent. So in the red and blue lines, we've just used two different shapes for like a peak in the power spectrum, but don't worry too much about that. That's just to kind of emphasize that a lot of these constraints are model dependent, and they can change by something like an order of magnitude, depending on how extreme you get with your models. So then, have we seen any primordial black holes, right? There's been a lot of attempts to look for primordial black holes, and just on the page at the moment, I'm not going to talk about them. It's just a list, like a non-exhaustive list of all the different methods that people have used to look for primordial black holes. And they can be broadly categorized into four different methods. Either we have lensing, so we look for light to be bent as if you're looking at a distant star, for example, as a black hole passed in front of it, it would lens the light from that star, and we look for that. We can look for the Hawking radiation coming from lighter black holes, because as primordial black holes give out Hawking radiation, they slowly lose mass over time. And as they get smaller and smaller, they give out more and more Hawking radiation, and we can look for the effects of that either today or in the future. Then we have dynamical constraints coming from how primordial black holes might affect the orbit of wide binary neutron stars, or how they might affect the structure of the galaxy. If you have, for example, very massive black holes flying through the disk of the galaxy, you might expect them to give kicks to stars and speed them up. And then there's a few kind of miscellaneous ones that don't fit into any of those. For example, you've got neutron star disruption, where neutron stars can be destroyed by basically being eaten by primordial black holes. And people have got quite exotic with those, and they've looked for signs that people could have been killed by PBHs passing through their brain, killing them. And we put all those constraints together, and what we get is this plot on the bottom. So we've got the mass in grams on the x-axis, and in solar masses on the y-axis, on the top of the x-axis, sorry. And we've got kind of constraints in their abundance on the y-axis, where the constraints is FPBH, which is the fraction of dark matter that can go to form primordial black holes. And as you can see, there are constraints on most masses, but there are still kind of a couple of kind of interesting open windows. Here you've got kind of the asteroid mass range, the lunar mass range, the stellar mass range over here, and here you've what's the stupendously large mass range, where they wouldn't really act as dark matter anymore because they're becoming, a sizable fraction of the mass of galaxies. But there are a lot of caveats to go into this, making this plot. So a single mass is usually assumed, clustering is usually ignored, and it's still a work in progress, right? And a lot of these constraints actually need updating already, even though this plot's only 3 years old. And so we've got a lot of kind of constraints on the abundance of different masses. And even though we've done so much kind of searching for primordial black holes, we haven't found any confirmed hints, confirmed detections, but there are still some hints for their existence. For example, LIGO Virgo Kuiper has been observing black holes merging for 10 to 20 years. They've been observed with unexpectedly high masses, unexpectedly low spins, and it's challenging to explain these observations with astrophysical models. It turns out it's also quite challenging to explain with primordial models. So it's not kind of a smoking gun that a lot of people might claim, but it's challenging to explain kind of why we're seeing what we're seeing. Then we have the detection of MACHOs, that stands for Massive Compact Halo Objects, in the 90s, where they were looking at kind of a source star in one of the Magellanic Clouds. And if a dark lens, such as a black hole, passed in front of that, it would cause a temporary brightening in the image. So as your lens kind of passes in front of the star, going from right to left in these consecutive images, it would cause a magnification of the brightness of the star. And they did see some evidence for dark lenses, but at the time they calculated it to make up less than 40% of dark matter, which is still quite a lot. Like if you kind of claimed you'd found a good evidence that like a quarter of dark matter was kind of this mass black holes, that's quite interesting. But nonetheless, there are kind of other models that could explain it. And finally, we have correlations between cosmic infrared and X-ray backgrounds. And basically, the infrared background comes from galaxies and stars which are too far away to resolve individually. So we just kind of see a blurry background of those. And the cosmic X-ray background comes from things accreting onto black holes. And this is from very, very early times. And we see strong correlations between the cosmic X-ray and infrared backgrounds. So the question then is, okay, well, why are there so many black holes at such early times? And where are they coming from? And it turns out that if you hypothesize a population of solar mass black holes, then you would expect to see structures starting to form around those black holes, and also forming the infrared background, and also matter accreting onto those black holes, forming the X-ray background. But it's challenging, without invoking primordial black holes, it's challenging to explain why there are so many small-ish black holes like that in the early universe. So we'll talk a little bit more about gravitational waves now, because some of the strongest evidence comes from that. So in Einstein's relativity, gravity is described as the curvature of spacetime. So large masses moving around can cause ripples in spacetime, okay, which is kind of what we're seeing at the bottom here. If we've got a binary system orbiting, as that system orbits and as those masses accelerate around, they send out gravitational waves. Now, gravitational waves are a bit weird. They're kind of best thought of as kind of ripples in spacetime. And what they do is they stretch space in one direction and squash it in the other. And kind of you get this kind of weird worm-like thing happening. And binary black holes will circle each other, because they're giving out gravitational energy, gravitational radiation. They will slowly lose energy and spiral in together, eventually merging. And these events are extremely, extremely violent. They're temporarily brighter than all the stars in all the galaxies and the entire universe. It's just that the energy goes into gravitational waves and we can't see it. And it turns out that any mass being accelerated will generate gravitational waves, just with a smaller amplitude. So large density perturbations sloshing around in the early universe would also generate a gravitational background, often called SIGWs, scalar-induced gravitational waves. And then have we seen any? Because if we form primordial black holes from large density perturbations, we should also form gravitational waves from those same large density perturbations. And actually, yes, we have seen evidence for some of this in the form of observations from pulsar timing arrays. Pulsar timing arrays use the same basic principle as kind of LIGO and Virgo and Kuiper. They detect small changes in distances. They're incredibly precise clocks, and basically as they spin, we can measure the time between them spinning, and they can cause gravitational waves to arrive slightly early or late. And if we monitor pulsars across many years and we look for evidence that there's correlated changing in the timing, that can reveal the existence of large-scale gravitational waves on nanohertz frequencies. And in 2023, the International Pulsar Timing Array, announced evidence for a gravitational wave background. And the signal they saw was approximately the right amplitude for primordial black holes to exist. Now, on the right, I don't want to talk about this too much, but the blue line on the top, these kind of curvy lines here, are kind of different ways that people have interpreted that signal coming from different models from scalar-induced gravitational waves. And the horizontal lines are the amount of the amplitude of the power spectrum we'd need for primordial black holes to exist. Now, depending on how we do that calculation and what do we use, we can either say kind of, in the top plot, there's, depending on how I do the calculation, there's an uncertainty of a factor of 3 in the amplitude of the power spectrum needed to produce primordial black holes. And we're only a factor of 2 away from having the right amplitude to explain the scalar-induced gravitational waves. And all I want to point out in the plots at the bottom is how much uncertainty there is in the calculation for primordial black holes. So depending on how you do the calculation and what parameters you use, there's a lot of uncertainty in there. So at the moment, it's too early to draw any solid conclusions. So it's all very uncertain and we need to do some more work on it. And I'm going to spend most of the rest of the talk talking about that, which I haven't got much time left, so I'll try and be very quick. So what we need to do is we need to understand the conditions necessary for primordial black holes to form. And that's key to constraining the early universe. So there are many different parameterizations we could use to describe perturbations in the early universe. We could describe a metric perturbation, zeta, or we could use the density contrast, or we could use something called the compaction. I can also smooth it and get rid of kind of small scales or leave them in. And there are also many different methods I can use to calculate that. And they all have a big impact on how much primordial black holes we expect to see and how we can constrain the early universe. So the curvature perturbation is a metric perturbation. Okay, it appears in, this is a kind of simplified version, it appears in the Freeman-Robertson-Walker metric as just basically a perturbation to the scale factor. We get this zeta here. And that's the thing that cosmologists normally use to describe the cosmos, right? Because it's generally pretty good at going from the curvature perturbation directly to temperature perturbations in the CMB, for example. Okay, so if we look at zeta and we look at kind of just a kind of a toy model, we've got a long wave perturbation, which is going to be outside the horizon. So it's super horizon scales, and we look at 2 small scale perturbations. Okay, now the idea is that these small scale perturbations might form primordial black holes, but the long wave mode isn't going to affect anything, right? Because it's way outside the horizon. It's just going to induce a time shift, okay, in the separate universe approach. But I don't want to spend too much time talking about this. But basically, when we look at primordial black hole formation, we should ignore super horizon modes. And if we just use the curvature perturbation, we're getting contamination from those super horizon modes, and we shouldn't. Okay, now on the bottom right, I've just generated kind of a random universe with random values for zeta at different points, and I've added in by hand one large amplitude perturbation in orange, which will be the perturbation that forms a primordial black hole. And you can kind of say, at least using the perturbation here, it's relatively easy to spot where that large amplitude perturbation is. Now, what you don't have on this plot is all of the, the very large scale perturbations, which are too large to fit on the screen, basically. So we're not seeing them. But I'm going to use the same universe in later examples to determine whether things are good parameters or not. So the first thing we could use is, instead of using curvature perturbation, we could just use the density, okay, which is given by this equation on super horizon scales. And the thing to notice is that it basically goes like the second derivative of the curvature perturbation. And that means that the density perturbations are dominated by small scales. Okay, so if I look at the same universe, so I've got this random universe here on the right, I look at what that looks like in terms of density, I just can't see a large amplitude perturbation that I put in by hand, this orange one, that's going to form a primordial black hole. So this is pretty useless to try and determine where primordial black hole is just using the density contrast. I can also go to nonlinear orders, and that suffers from all the same problems, but it also adds in extra complications because the statistics of this thing, sorry, I'm losing my voice. are much more complicated. And also there's some weird effects where, because of that time shift I was talking about, this kind of larger scale perturbation here is actually damping the density perturbations inside that region. So it's can also give you really confusing, complicated, and also misleading results. So that's not a good choice for the parameter. So what we want to do really is we want to get rid of those perturbations, and we do that by what's called smoothing. So we just kind of take, okay, I'm going to look in this region here, for example, and I'm just going to take the average value of the density in that region. And what that does is hopefully it gets rid of the small scales. And there are various different ways that we can do that. We can use kind of different window functions, which look like these. And it basically just says how I take the average within a certain volume. Okay. And if we do that, we get something called the compaction, but I'm running out of time, so I'm going to gloss over it because I think I'm about out of time. Okay. But basically, if I use the top hat window function and I use the same universe, and basically what I'm doing now is increasing the smoothness scale and looking at my perturbations, okay, I can still kind of see my large amplitude perturbation when it starts to appear. I can still kind of determine when my primordial black hole forms, but you see that as we go on, we're not really very effective at getting rid of those small scale perturbations. And my universe is always dominated by those small scale perturbations. So the top hat smoothing isn't ideal, but we do have a nice analytic control over the problem base, so that's good. We could use a Gaussian smoothing function, and that's in general much better at smoothing out. So as I increase the smoothing scale now, and I look at what my universe looks like, it's very good at isolating the specific scales, where I've only got perturbations of the scale I'm looking at in the plot left. So I'm very good at isolating different scales, but this is much more complicated analytically. So with the top hat window function, it was quite complicated already, but you can get a relatively nice kind of expression. But with the Gaussian smoothing function, you can't. So the question is, which window function is correct? Which one correctly encodes the relevant physics? And we don't know. There's no kind of a priori way of arguing which one. So I'm looking at the effects of different scale perturbations on primordial black hole formations in order to determine like how we should effectively smooth the distribution. And really quickly, how do we calculate the abundance? There are basically three different ways. Okay, so the simplest is called threshold statistics. We basically want the caveat that primordial black holes form in regions above the threshold density. So we just have a step function where if delta R, so if the density perturbation in a region is above some critical value, so if this inside the bracket is above 0, then I will form a primordial black hole.
Hello.
Otherwise, I would. Hello. Yes, I've got like 2 slides left.
Yeah.
I'll
Okay.
be very
Fine.
quick. Okay. Okay. So we can do that, and we can calculate it that way. That's relatively simple. Like this is the full expression down here on the bottom. Relatively simple. It's just an integral over your probability distribution function, and here I've assumed Gaussianity. However, there are more complicated things I could do. So as well as requiring that, the density needs to be above a certain value, I could also say, well, primordial black holes are going to form at peaks in the compaction and the density above some value. And that means I want to add in some extra conditions to where primordial black holes form. Okay, I want the first derivative to be 0 because I'm at a peak, so the spatial gradient will be 0, and I also want peaks and not troughs, so I want the second derivative to be negative. Or we can extend that even further. That's the theory of peaks. We can extend the theory of peaks, and we can say not only will primordial black holes form at peaks in the compaction in space, they will also form at the scale where the compaction function has a maximum. Now, don't worry too much about what that is, but basically this is saying that a primordial black hole will form at the scale where the perturbation is the largest. So we add in 2 more conditions, and these make the calculations significantly more complex, but they theoretically make it more accurate. And theoretically is often quite a worrying word because we really don't want to just kind of do things theoretically. We want to have some way of comparing these and looking at data and seeing which one is more accurate. So which method is correct? Which one correctly encodes the relevant physics? Again, we don't know, but it's what a lot of my research is focused on at the moment. So a quick summary, we don't know what most of the universe is made of, what are dark matter and what is dark energy. We don't really know. We've got a lot of ideas about kind of, what dark matter might be, but nothing conclusive. Primordial black holes in a certain mass range are viable dark matter candidate, and they've got a wealth of interesting phenomenology. And it's possible we've already seen a lot of evidence for their existence. And gravitational waves are becoming a precision probe of the cosmos and PVHs in particular. And upcoming detectors in the 2030s will provide a wealth of new information, hugely improving our constraints and our ability to constrain smaller scales. But there's still a lot of theoretical work to do before those new observations can be used to their greatest effect. So I'm going to stop there, and I'll just leave up a slide with kind of some more